week 7, potential energy and kinetic energy. And we have been talking about work and energy. Energy is the ability to do work, or if you look up in dictionary, it says vigor or capacity or the power, and that all relate to the energy. But scientifically, in the physics, energy is the ability to work. And then what is work then? And the work is the process of the energy transfer. And there are all different forms of work, and so do different form of the energy. So in the mechanical physics or in Newtonian physics, work is defined as force times distance. And then we had the work and energy theorem, which is energy gain is of an object is equal to the kinetic energy increase. So that's similar to that momentum impulse theorem. And an impulse is equal to the momentum change. Now here the energy gain is equal to the kinetic energy change. So the interpretation of this is if you have a force applied to an object, then for a certain distance, then that work is simply this times the distance. And the physics interpretation of this process is that whoever applied this force and provided the energy from their body or chemical energy turned into mechanical energy. And then through the work of force, then the energy goes into the kinetic energy of this object, or the kinetic energy in turn lost into friction between the up block and the ground. So all that is good. So now there are 4 phases of matter: solid, liquid, gas, and plasma. Solid have the definite shape and volume. The molecules are relatively fixed distance from one another. They sometimes organized in a very nice array like this, and we call it crystal. And for example, a silicon atom, and the most abundant substance on Earth, is ordered like a hexagon structure if you look from one profile. And then they bond together in the solid. They are very close together. Liquid, on the other hand, the molecules are still close together, they bond together, but they can move around. From outside, look macroscopically, and they don't have definite shape or volume. They can flow around each other like water. Okay, but if you zoom into microscopic world, which means and the molecules are still close together. They are packed, but they can just slide around each other, but they can't move around. But it's basically close packed. That's the general picture of liquid. Gas is different, and when the temperature is high and pressure is low, and then this phase, there are weak cohesive forces between molecules, or rather the kinetic energy, the motion overwhelmed the attractive force, so they are separate into the space around it. They have no definite shape or volume, and they move in random directions, and the speed and are influenced by their collisions. So that's the picture you have. And you can see a video, or in the lab, we see that's the general picture in a gas. Well, in other words, there's a lot of space between molecules or atoms. They move in different speed, different directions, they collide, or they bump into each other all the time. But they have a speed, and here's the word. If the speed has different and random directions, we say mathematically we have a speed distribution or velocity distribution. Another phase, the fourth phase is the plasma phase. And plasma means something just smeared out in general. If you look up a dictionary, it means just And then here, particularly, it means positive, negative ions, which means they are separate. You know from chemistry that in normally substance, the positive protons are surrounded by negative charged electrons. They are very close together. Okay, if we rip off the electrons off from the core, from the positive core, they separate, then you get ions. So in this case, the plasma is gases, but they are basically ion and electrons, and normally very high temperature. And they conduct electricity and interact with magnetic field. So these are the situations that can create electrons. So you put a grape into microwave because the conducting material, so it's so hot that you get this ion. That's actually plasma. But usually we experience three different type of phases: solid, liquid, and gas. Plasma, you can make it in special situations on Earth, like this toy you probably see, and this in the microwave. Sometimes things turn into plasma, but just momentarily. But if you look into study astronomy and astrology, not astrology, astronomy, in sun, in some other stars, basically all plasma. Okay, so it's not uncommon actually. Everything on the sun is in the form of plasma. Converting temperatures. We have been talking about the temperature is nothing but the kinetic energy of the molecules, or average of the kinetic energy. The real characterization is connected to the Kelvin degree. Basically, is average of the kinetic energy of each molecules. But velocity is very fast, but average is regular number, squares, always positive number, but the mass is very small. So this temperature, the kinetic energy, is very low, very small. Now to scale up to a more comfortable number, can be used for our daily life, and Boltzmann et al. Used a conversion constant, and this Boltzmann constant, which is a very small number. Over here, that's kinetic energy of average molecules, but divided by a small number, so let's scale up to some regular numbers. Not only that, this number is chosen such that the temperature, the Kelvin degree, has just exactly 100-degree difference between the ice point and the boiling point. And in particular, at ice point is 273.15.
Hi, this is Frank with A Plus Security Center.
And 1.5. And then at the boiling point is 300.75, exact 100-degree difference. If I ask you why exactly in Kelvin degree there is a 100-degree difference, and you have to ask Boltzmann, and you can say, well, it made that way because it adjusts this constant, so this new temperature scale, it is kinetic energy but scaled with a constant. So the constant is fixed. You can look up the Boltzmann constant value, which is something very tiny number, but that will scale this temperature to the Kelvin degree. And characterize the Kelvin temperature is that 0 degree is absolutely no motion. So then it's no velocity. Everything is dead. So, but can you have a negative Kelvin degree? No, because something squared over here can never be negative. And then, so at worst case, everything is frozen and not moving, it's 0. So, and of course everything is go. So therefore Kelvin degree is always a positive number, and lowest is a degree. So now associated with that, then there's a Celsius degree temperature. And if essentially it is Kelvin degree, but I just don't want to use this number, 275.15, you say, well, that's the freezing point. Let's call that 0 for Celsius. And then degree for degree match, and then every time Fahrenheit go up 1 degree, Celsius go up, and then the Kelvin go 1 degree as well. So therefore, Kelvin temperature and the Celsius temperature are essentially the same temperature, but except that the Celsius are invented to make it convenient. So 0 is the freezing point, 100 is the boiling point, and so on. So then we have the conversion between Celsius and Kelvin, pretty easy. So simply self plus this number, and you get Kelvin. And backwards, Kelvin to Celsius, subtract 275.15. So, and vice versa. So that's the conversion. And then we have Fahrenheit temperature degree, and that is the empirical temperature, and it's characterized that its freezing point is some kind of a salt water, the water you use to make the pickles, and when you add that kind of salt into water, its freezing point is very low. It's below where ice freeze. So that point is Fahrenheit degree 0. So, but turned out that that became the most popular temperature we use in US and some other English-speaking or Canada. So then Fahrenheit converting to Celsius, and then you have this formula. But one teacher point to remember is that 32 degree Fahrenheit is freezing point, and then something like 212 is the boiling point. So these are the two formulas. So now we mentioned the 3 different temperatures. Out of the 3, you have 3 choose 2, and you have 6 different conversion relations here. So remember, I'm not asking you to force you to remember exactly, but just get the concept. You can remember easily. Whenever there's a test or something, these conversion formula are available and easy to use, but then it's good that you can remember it. All right, that's it. So this is the recapture what we talked about in the class. These are the temperature feature point, and 32 degree. Let's talk about the Fahrenheit first. 32 degree Fahrenheit is the ice point, and boiling point is 112 degree Fahrenheit. Actually, I myself is not quite familiar with this, but well, Imani, she knows. And then fever, and what temperature considered fever, and you say 102, and that's cool. And what's the normal temperature is around 98. So that's the Fahrenheit, and the temperature that we most familiar with here in United States. And so then Celsius. Celsius is nothing but absolute temperature rescaled. Ice point is 0, and 100 point is the boiling point. And with fever, and that's good to remember if you go to another Europe or Japan or China or any other Asian country, they use Celsius. So 37 degree is low fever, and temperature 37 or 36, and 39 is kind of high fever, 40 is even high, 42, you better watch out, it's very dangerous. Normal temperature is about 36 Celsius. And Kelvin, and of course, once again, 273.15 positive is ice point, and then add another 100 degree Kelvin, you get 373.15, and that's the boiling point. And then if you want to see what the absolute temperature from Celsius, all you have to do is add this magic number, 273.15. So we did a conversion between numbers. So this the formula is still in the previous slides and pages. And from Fahrenheit to Celsius, you simply do 5/9, which is a very almost half, and then parentheses Fahrenheit minus 32. So we tried with 0 degree, so you have 0. And then the other way around, backward from Celsius to Fahrenheit, you have 9/5. Usually, and also just remember that the Celsius is larger step. So therefore, and 9/5 is about 1.8. You multiply that, and then plus 32, because the 0 point is at 32 in Fahrenheit, and Celsius. So you, for example, 32 degree, that's a little bit low fever, and then you have 32 times 5, 9, and then plus 32, and then you end up with something like 102.2. So you will get this question. These are simple questions. I'm sure I encourage you to get all of these questions answered correctly if you ever you've ever been asked these kind of questions. Converting between temperatures. Another important concept about condensed matter material is the pressure. Pressure looking from outside or macroscopic is force divided by the area, which means imagine you put your hands on a table. You exert a pressure on the surface. So then the bigger the force and the bigger the pressure. Now, imagine your hands is smaller. A smaller force and then smaller area, the same force, and then divided, and then you have bigger pressure. And you use the same force, but if you use a thumb or pointer to put at the table, and then that's a stronger pressure because of the small force. So force divided by area. Therefore, force in the units of newtons, area in the meters squared, square meters. And then, so the standard units for pressure is newtons per square meter. In other words, how many newtons are there in every square meter. Of course, you can change the units, converting it. And that unit is called Pascal. Once again, the standard units of pressure is Pascal, newtons per square meter. So here is once again another idea, and you have same force if you use small pressure with the finger, if you point that small. Then compared to use as a needle with the same force with the finger, because small area and you will have stronger pressure, and larger area, and compared to the needle, your finger has larger area, and then you have smaller pressure. Okay, and of course the tissue will stand a certain pressure. So pressure is force divided by volume. As units is newtons per meters, but it is called Pascal. Now, let's look at the origin of pressure. So we're looking from the receiver side, and what causes pressure, and microscopically. And so there are three scenarios. Okay, and most commonly seen is a solid contact. Like I said, you have a needle touching your tissue, or your hands put on a table, or one surface exerts force on another surface, contact. So then you can have pressure. That's called static pressure. But within the solid, so inside the solid, there are forces, which means this part of the solid, think about a piece of bread or ice cube, you talk about pressure inside. Okay, and in fact, interestingly, there's no pressure can be defined, but doesn't mean there are no force. But the force is not defined by a pressure. Rather, there are stresses. Okay, pressure is like the force is perpendicular. If you slice a surface, the pressure is the force actually perpendicular to this surface. Okay, and if you have a surface this way, the pressure is actually that way. The force will be that way. But within solid, there is no pressure. but in general, if you imagine you slice a surface within a solid, actually the force is not perpendicular to it. Actually, that kind of force is called stress. Should be described by another quantity. By the way, pressure is a scalar quantity, even though it has the force exerts surface. It's a scalar, which means it does have no direction, but it's just a number. But in the solid, and then there's the forces and there are surfaces, and you cut different profile surfaces, the forces are not necessarily perpendicular to the slice. Then therefore, there's no pressure can be defined. Rather, it can have a stress in the which is anisotropic. The word isotropic actually means it's same in all directions. Anisotropic, in the solid, you can have stress or shear forces. Although we are not getting into that, but you realize that within a solid, there is no pressure can be defined. Rather, the force within the solid should be described by another quantity, which is called a tensor mathematically. Now, in liquid, things are simple. Pressure can be defined, and a pressure in a liquid is actually isotropic, which means, for say, in water, the pressure is at a certain depth is all the same. In other words, if you imagine you slice a surface in the water, and it has the force is always perpendicular to the surface you imagine. So it's all directions. Although in the fluid, it is weakly dependent on the temperature. So pressure in the liquid is isotropic. It means all directions. For example, in our lab, the pressure at certain depths is only dependent on the depth. But at that depth, you say, well, the pressure, you can't say pressure is in which direction. But imagine you have a surface, you slide the surface, it's always perpendicular surface, there's a force, and it's balanced, okay, by the Newton's third law. It's pressing to each other. So then that's all right. Got to cut off a little bit from previous slides. We talked about gas pressure, and gas pressure is basically due to the collision of the molecules. Collision of molecules over the surface. Basically, like we did in the lab, we see that the molecules are moving with very high speed, and at the same time they hit each other, collide each other, and that's when their momentum changes. It exerts impulse on the walls or any surface, stick on the side or inside the gas collection. So, and they bending on the walls. Basically, that's the origin of the pressure in this solid. And then we live on Earth, and there are air around us, and that air has gravity, but there are like around 20 miles of air outside. We are under that blanket, if you can imagine. And then there is, because gravity of the air, we have the pressure due to the atmosphere pressure. That's pressure due to the air. That's called standard atmosphere pressure, is about 101,000 pascals, or we can say 101.3 kilopascals, and that's something to remember. And later we're going to compare many things like pressure of the tire, and if you dive into water and what's the pressure increase, we've all sort of based off this number compared to this number, because that makes sense. So now, quick summary of what we did in class, and these are the exercises about pressure. Now, as a woman walks, her entire weight is momentarily placed on the heel of her high heel shoes. Calculate the pressure exerted on the floor by the heel if it has area of 1.5 centimeters squared, and the woman's mass is about 55 kilograms, express the pressure in Pascal. And so we know that, okay? And then simply you will say that the solution is the force divided by the area. So then 50 kilograms times 9.8, that's gravity force on the hill. So that's this much newtons. But then divided by the area, 1.5, well, it's in principle it's right, but pay attention to the units. In fact, and it is the units that's important in this. So the concept we know already. So it's not simply this 5.39 divided by 1.5 and that's it. But that you will get the answer with newtons per centimeter squared if you need that unit. But if you want to answer in Pascal, then you will need to convert units. So here is how you convert units. 1 centimeter is 0.01 meters, 10 to the negative 1, 10 to the negative 2 meters. But then square meter, square centimeter, then you have squares. So now you work a little bit of math. This 2 will go over to the 0.01 squared and 0.0001. So 10 to the negative 4 meters squared. So 1.5, 10 to the negative 4 meters squared. So that's the area. And then you divide it by. Okay, now here's the little math review. If the length is scaled by, say, 100, and then the area will square by 10,000. So imagine this is the 100 by 100 centimeter square, and that's a meter square. And then there are actually 10,000 of these tiny squares instead of 100 only. Okay, that's when you do linear. You have, if you do a volume later on, it will be times another 100. Okay, so then once you do that, you divide these two numbers. So 593 divided by 1.5, 10 to the negative 4 meters squared, and then you get 3.5 times 10 to the 6 Newton meter per square. Newton per meter squared. That is quite high pressure. But then we talk about, well, how high is? Well, if you think about atmosphere pressure, it's very high also. Then if you divide by 101.3 kilopascal, so then you'll get 35. Okay, roughly compared to air pressure, that's the hill gives such high pressure that it's 35 times high, 35 to 36 times higher than atmosphere pressure. So that's this question. That's the point. How high the pressure is. Of course, in early days of the commercial flight, women are not allowed to wear high heel shoes because the aircraft floor are too thin to withstand such high, large pressures. You sort of poke holes on the floor, and the flight attendants or the airline would not like it because they damage their plane. Okay, and that's reasonable. Okay, now next question. Nail tip exerted on a tremendous pressure when they are hit by hammers. So basically nail tip, and why you want a nail? Why you want to be a flat tip? No, because a sharp tip, a small area, and the small area, and then with same force, and it will give you larger pressure because they exert large force over the small area. Okay, what force must be exerted on a nail with a circular tip of 1 millimeter in diameter to create a pressure of this? That's 3 times 10 to the 9 Newton meter squared. That 3 times 10 to the 9 Pascal. This high pressure is possible because the hammer striking the nail brought to rest on a short distance. You know, it's high impulse. Again, it's the same relation applied, but this time, whenever you have a quantity, you have equation, you have 3 variables. If you know 2 of them, you can find the other one. In this case, the pressure is known, the area is known, but we are to find the force. So therefore, the force is actually equals the pressure times the area. Okay. Then, but in this case, pressure is already known. we're asked to how much force it should be. But then there's a little bit complication in how to calculate the area. So that's we are giving a circle. It's a circular. So giving the diameter. So you recall that to calculate the area of the circle, all you need to do is times pi radius squared. So let's continue this on another page. Remember, we know the pressure and we know the area. We're going to calculate the area of the circle with the 0.1 millimeter in diameter, and then we're going to multiply the pressure with the area. We get force. So let's just transition to the other area, the other slide. Well, let's continue on this one. The area is a little circle. It's pi radius is a diameter divided by 2 and squared, and that is how you calculate the area. But we leave this complex here, and then now we go back to our equation: pressure, force divided by the area, which is that part, and then you multiply this, which is area, to the force. Then you have the force will be equal to this. Then you multiply this out and work out the math. Then the force equal to 5.1 times 10 to the third newtons. That is about 1 newton is 1 kilogram is force is about 10 newtons. So this will be like 500 kilograms roughly. So think about it, or like now 1,000 pounds weight force. So that's the force need required on that nail. So it's quite strong. So you swing the hammer, and that very moment the force will be like 1,000 pounds on the nail, but only for a moment. That's it.